My talk is about Lorentz force MEMS magnetometers. There's several applications for magnetometers, as you saw in the previous presentation. One of them is in automotive applications. There's also applications in navigation for electronic compasses that you find in most smartphones today. Applications for satellite navigation. There's also a lot of biomedical applications for bioimaging of things inside the body. For example, if you inject some sort of magnetic material inside the blood, you can follow the blood flow inside the body using magnetic sensors. Or one of the areas that's becoming of great interest these days is mapping of the human brain, because neurons inside the brain, when they fire, they generate these small currents that if you have a very sensitive magnetic sensor, you can detect them and you can basically find out how the brain is acting or detect some problems before they happen. So a wide variety of magnetic sensors are available. Hall effect, we are probably all familiar with, which is used to detect magnetic fields mostly in semiconductors. There's GMR, AMR sensors. The previous presentation was about AMR. The flux gate. The flux gate is another type of magnetic sensors. Now, the AMR, the Hall effect sensors can be miniaturized on chip, but the flux gate is harder. There have been efforts to make MEMS versions of flux gate sensors, but it's, as you can see, because of the coils, it's really hard to miniaturize this type of sensor. And then there's search coils and squids, which can be extremely sensitive, but you can see it's really hard to miniaturize them. The squids are not that big themselves, but all the supporting cryogenics that you need to support them is really power hungry and large in volume. So here you can see different types of magnetic sensors and the sensitivities they can get to. Hall sensors are not that sensitive. AMR, GMR, and MEMS. So far what we have for MEMS is within this area. There has been some new work that has expanded this quite a lot, but the traditional Lorentz force magnetic sensors are pretty insensitive compared to search coil or squids. So the goal of this project is we're trying to push the sensitivity of MEMS Lorentz force magnetometers all the way down to the picotesla and even femtotesla to be able to compete with the squid. So instead of having a big cryogenic device which takes a ton of power, if you can replace it with a MEMS device that is easily portable, or you can even stick it to someone's body to detect biological magnetic fields, that would be of great value. Now, advantages of MEMS, of course, we all know: small size, lightweight. It's portable. The problem is right now, the Lorentz force magnetometers that are available are 5 to 6 orders of magnitude less sensitive than squids. So how do we cover this gap? Well, first of all, a little bit of introduction about Lorentz force magnetometers. So Lorentz force is the force that is applied from a magnetic field to a moving charged particle. So basically, if you have a current flowing inside a conductor, and you expose it to a magnetic field, there will be a force applied to those charges, which turns into a mechanical force applied to that wire. You can use that as an actuation force for a mechanical structure. Now, most of the time to detect Lorentz forces, people use resonant structures. What is the advantage of a resonant structure? Well, if you can actuate the resonant mode as opposed to just applying a DC force to a structure, you can get much larger displacement amplitudes. For example, if you have a resonator with a quality factor of 1,000, you can get 1,000 times more vibration amplitude if you excite the vibration mode. That's why typically Lorentz force is applied as an AC field or as an AC force to a resonant structure, and once you excite the vibration mode, you can get much higher sensitivity from that. Now, there have been many designs, several designs for Lorentz force magnetometers. This is the one we are using, which doesn't actually seem like a very nice design. So this was supposed to be an animation. Unfortunately, it's not working. But the way this is supposed to resonate is that these two plates move out of phase with respect to each other, so they move up and down, and the beam that is connecting the two plates would be stretched and compressed. Now, this is not a very good design for a Lorentz force magnetometer because typically you want a Lorentz force resonator to be very soft because you want to get the maximum possible amplitude from the minimum amount of force. In this one, we have these two plates connected by this rigid beam in between. As you can tell, this beam is being stretched, so it has a very high stiffness. Why would you use such a stiff structure to detect Lorentz forces? Well, the answer is because we can get a lot of advantages from this. First of all, we use piezoresistive sensing, so this beam acts as a piezoresistor. But also, as you will see in the next slides, this can act as an internal amplifier and really amplify the vibration amplitude. Now, how does that work? So this animation is working, which is great. So you can see the beam is being compressed and expanded because of the vibration in the structure. Now, if we look at this loop, if we have some vibration because of the Lorentz force coming in, so if we have an AC Lorentz force at the right frequency, which excites the vibration mode, you get a little bit of vibration. That vibration modulates the resistance of this beam because of the piezoresistive effect. Now, if you have a DC bias through this or across this wire, so if you have a DC current flowing into this beam, because of the compressive and tensile stress that is caused by the resonance, the resistance of this beam would be modulated. Now, that resistance modulated times the current, the bias current which is flowing in there will give you a power component, a Joule's heating component that will be changing with the same resonant frequency as the structure. Now, if the phase of this heating is right, it can amplify your motion. So basically, what you have is a spring that when you stretch it, its resistance increases or decreases, so it cools down and it wants to compress back in. And when it's compressed, it will heat up and tries to push back. So it's not a passive spring anymore. It's like an active spring, which takes some power from the DC source and actually amplifies its own vibrations in a way. So you get more and more amplification. So what you can do is, by applying a tiny amount of force, this internal amplification can give you a lot of vibration amplitude if it's done properly. Here's another demonstration of the same concept. So basically, displacement gives you a change in resistance. That gives you a change in temperature, which helps the displacement. Initial displacement is given by the Lorentz force from the magnetic field. And then within this loop, you can amplify the vibration amplitude. Theoretically, you can amplify it by even 1,000,000 times. There's no limit to it. But in practice, we have shown up to 10,000 times, but not in this work. So here's the schematic view of the device. Again, you have the two plates and the beam that does the amplification in between. We have this metal layer on top. So the structure itself is made of silicon, and we use gold wires on top. So the gold wires are to pass a current. It's an AC current to give us the Lorentz force. So if you pass an AC current through this wire and then have a DC magnetic field, you will have an AC force which is trying to actuate the resonator. And then once you get the resonance, this beam will amplify it, and then you can pick it up through silicon between these two pads with the piezoresistive effect that you will see across the same beam. So here's another demonstration. This is the picture of the fabricated device. It's hard to see the gold versus silicon. They're the same color, but so basically you have gold in all these areas, and this is bare silicon. The fabrication process is pretty simple. We start with the SOI substrate. There is a nitride layer patterned on top. The nitride acts as isolation between gold and silicon. So we pattern the gold with by liftoff, and then the nitride is etched away, so it's only kept under the gold. And eventually the silicon is patterned and undercut. So you'll have this suspended silicon structure with the gold on top of it, which is also insulated from it by the silicon nitride. This is the zoomed in view. You can see the beam here, which is pretty narrow. You can see the gold layer here. I guess that's about it. Now here's the measurement results. So This is with a magnetic field of 9 millitesla, which we have applied to this device. This is the device with a very small amount of DC current going into that beam. Remember that beam that does the amplification? So this is what it does if there's almost no amplification. Now, as you keep increasing the DC current in the beam, you can see the effect of internal amplification showing up. Now, you get some amplification simply because you are putting more current into the piezoresistor, so that gives you more signal. But at the same time, you can see that the peak is becoming sharper and sharper, which means that you are actually compensating the quality factor of the resonator. You are putting in some more energy from the DC source into the resonator, which increases the quality factor. You can see the quality factor initially was about 500. This is operating in air, no vacuum. And as you keep going up, the quality factor reaches 13,000, which is not that high, but it's 28 times improvement compared to what it was originally. So this is the intrinsic mechanical quality factor of the device, and this is how far we have been able to push it. Theoretically, you can go even higher. The problem is if you keep increasing the current, at some point it will just burn because the heat becomes too much. You won't be able to take it. But if you design the device properly, you can potentially get a lot more amplification from this. So this is all measurements with the same field. This is measurements with the same current, the maximum current of 28 milliamps, which is the current passing through that beam amplifier, and with different fields. Here you can see the graphs of sensitivity. This is the original sensitivity without any internal amplification. It's about 1.4 millivolts per Tesla. And so the slope of the line shows sensitivity. And eventually, by increasing the current from 1 milliamp to 28 milliamps, because of the internal amplification, we get up to 1 volt per Tesla. Now, it is not a very high sensitivity. For this device, we can barely get under 1 microtesla, so it's not nearly as sensitive as we want it to be. But the goal of this work was just to show this concept of being able to increase the sensitivity by adding this internal amplification. And then here you can see the effect of Q-amp, because what is increasing your sensitivity by 700 times here is not just the internal amplification, it's also the fact that you are putting in more current. So in this graph, you can see the effect of current taken out, and you can only see the effect of quality factor increasing. So this is only the effect of internal amplification, which is about 30 times as well. So I'm going to skip the conclusions. And so basically we showed about 1,000 times improvement in sensitivity by internal amplification. And I would like to thank the U.S. National Science Foundation for funding this project. Thank you.